Today we're going to discuss energy as pertains to nuclear chemistry. Specifically, we're going to be looking at two kinds of energy production that you can get through nuclear processes. We're going to talk about fission and about fusion, and this is a really important subject because we're running out of energy. A lot of the energy that we've used for the past couple hundred years has been in the form of carbon that's been sequestered underground for a lot of years in the form of coal and oil and natural gas. Eventually we're going to run out of those things. It takes too long. Those are non-renewable resources. So we have to start looking at some other places where we can get our energy. So one place that we can look, and we'll discuss a lot of the advantages and the disadvantages to it, is into nuclear energy. And so today we're going to see how nuclear energy works and what some of the benefits and drawbacks are to the various types of nuclear energy, and what we might need to do about that. So we're going to start with fission. Fission, as you know from the vocab, is the process of splitting a heavy nucleus. And we have a simulation on here that we looked at before, and we'll look at it again. Here we have a uranium-235 nucleus. It is fairly stable, but it will break down if you let it, if you shoot a neutron at it as such. And when it does break down, you can see it gives off that big burst of energy. It gives off a lot of energy whenever it's almost like a big coiled spring that neutron releases. And you can use this to make energy. And so if you have a whole bunch of uranium-235 energy neutrons, or not neutrons, woo! If you have a whole bunch of uranium-235 nuclei, notice that one of the things that happens is that nucleus shoots out neutrons when it splits. And when it shoots out neutrons, those neutrons hit other nuclei, which cause them to split, cause them to give off more, and then you get what we call this chain reaction. And you can see a huge amount of energy given off. It's a self-perpetuating process. That's one of our vocab words. It's a chain reaction. You just saw the chain reaction there. If we do it again, you can see it again, and you can see a whole lot of energy given off right there. Now, that is a uranium-235 nucleus. It's a particular isotope of uranium. Has 92 protons and 108 plus 35, 143 neutrons. And if we try to do the same thing with uranium-238, which is another isotope of uranium, has 3 more neutrons. If we try to go ahead and shoot now, you'll see that uranium just became uranium-239, and it didn't do anything. It didn't split, and we're not getting energy out of that. So we cannot use uranium-239 to get this energy out. It is not fissile. Fissile is one of the words that we need to know. F-I-S-S-I-L-E. Uranium-235 is fissile, and uranium-238 is not. So that word again, fissile. Fissile essentially means that you can get energy out of it through fission, because it will readily release, can get into that chain reaction. So uranium-235 is fissile, and uranium-238 is not. So what we just saw there was where the energy for nuclear fission comes from. It's trapped in the nucleus, and then the neutrons allow it to come out. And so we need uranium-235 for fission to take place. Now, so what we do then is we go out into the mountains and we start digging up this uranium stuff because we need it to make energy. And we go pull out, like, let's say you pull out 1,000 pounds or grams or kilograms or whatever unit you want to use of uranium. Unfortunately, what we find when we do this, if we go mine a bunch of uranium, not all of it is 235. A substantial portion of it is 238. In fact, I believe it's 99.7% of it is uranium-238, the stuff that is useless for us to make fission happen. And so that leaves about 0.3% is the uranium-235 stuff. So you can think of it this way: you have to take 1,000 out of that 1,000 pounds of uranium you just dug up. You can get about 3 pounds of fissile material of the uranium-235. And so not only is it hard to get very much of it, it takes a lot of it to get it, but you have a big problem. Once you have it out, you have to separate it. You have to, they call this process enrichment. It's what the Iranians are currently in 2012 trying to do, is to come up with good ways to enrich their uranium so that they can make these power plants, is what they say they're going to do. And so there are a couple of ways to do that. Probably none of them are simple, but the simplest way to describe it to you, whenever you enrich uranium, you take all of their uranium. Oh my, that's not good. That's supposed to be a T there. It's not cooperating with me right now. Whenever you, what you do is you take all of the uranium, which is a solid, it's a metal, and you react it with fluorine to make this uranium hexafluoride gas, UF6. And that's a gas, and so you take this gas and then you can essentially, they call this diffusion. You can take this uranium and you can put it through a diffusion tube. And what that means is you take that uranium hexafluoride, that UF6 gas, and it's a mixture of both the 235 and the 238, and you put it into this chamber through this little pinhole, and you have another pinhole on the other side, and it diffuses. It just kind of spreads throughout the cylinder until it reaches the other side and exits that hole into another gas cylinder. And what's the point of this, you might ask? Well, the point is that uranium-235 is very, very slightly less heavy than uranium-238. Therefore, it moves slightly faster. So if you can push it through this tube, while you might have 99.7% uranium-238 here and only 0.3% 235, by the time you get over here, you may have a slightly higher percent. You'll get like 0.5% or 0.6% or something. And then you put it through another tube and the percentage becomes a little bit higher. And you do that enough times and you can get pure uranium-235 out of the end. Just because let's say the red uranium-238s don't move as fast, and let's imagine the green is the 235s, and just because they're slightly lighter, they'll get to the other edge a little bit faster. And so there'll be slightly more of them as you leave, and then you do that again and again and again, and that's one way to enrich uranium. There are other, if you read about it in the news, you'll hear about centrifuges and other things like that. We don't need to get into all of that, but that is a process of enrichment. So once you have your enriched uranium, then you can begin to make what we call, you can make a nuclear reactor. And the way a nuclear reactor works, the way that most energy works is you essentially got to boil water. If you can boil water, you can make energy, because the water goes through coils and pushes a turbine and rotates a magnet inside a coil, and that's how you get your energy out. That's how AC current is made. So you're just trying to get something hot, trying to boil some water. So how do we do that with nuclear reactions? This is how we do it. We have a little diagram here of a nuclear reactor, and there are two independent parts here. There is the control rod here, and then you have the fuel rods. These vertical columns, these green areas in here made of uranium-235 nuclei, those are your fuel rods. And so you have a fuel rod, fuel rod, fuel rod, fuel rod, fuel rod, fuel rod, and then those blue areas in between, those are control rods. So the fuel rods are made of uranium-235, and the control rods are going to be made out of like cadmium or boron. And the reason those are important is because they absorb neutrons. And if you recall from our previous demonstration, neutrons are the key. They're the trigger to this nuclear reaction. So if you can get neutrons going in here and hitting all these nuclei, you're going to get fission. But if you can stop the neutron flow, then you're going to slow down the process, because you don't want the process to get out of control. You don't want the whole thing to get overheated, melt down, and start spewing all of this radioactive stuff into the air. So you can see here how the control rods work if we start the simulation. If I go ahead and fire a neutron, you can see that some of the, that not a whole lot happened. Not very much happened there because I have the control rods all the way up. And so whatever neutrons get kind of shot, they kind of get absorbed by one of the blue rods. You see that? And you make just a little bit of power. So if I want to make more power, I can lower the control rod, and now whenever I fire neutrons, they are not, those blue things will not absorb the neutrons, and now there is more flow between the fuel rods, and you can see now we're getting a lot of energy out. And we can go ahead and stop it if we want. We can pull that up and we can watch the energy slow down and stop, because now we have stopped the flow of those neutrons. And so as this happens, all this energy is being made, this is getting hot, and that heat can boil water. And you can actually look at a picture, I don't know if you can see it very well on here, but that's a picture of this underwater nuclear reactor. You can see the control rods down there. But again, this is a PhET simulation. You can go look at it yourself if you like. So that is how fission works, and that's how the control rods control the reaction. Now there's a couple of big problems with nuclear fission. First and most obvious is that you don't want something terrible to happen. You don't want these control rods, these fuel rods to melt down. This happened famously in 1986 in Chernobyl, Russia. It was a place that had a nuclear power plant, and they ran it well past what the safety features said that they should be running it, and the whole thing melted down, blew the cap off of the thing, and spewed radioactive waste into the air and scattered it through rain over hundreds of thousands of square miles. It was probably the worst nuclear disaster based on a nuclear plant that's ever happened. And the entire town had to be evacuated. A lot of people died immediately, and then even more people died through the radiation exposure through time. And so that's a real big concern. And newer plants are built with a lot more safety measures in mind. And even when I taught this a couple of years ago, I would have told people that I thought that nuclear power was a lot safer than it used to be, and I suppose it is. But just about a year ago in Japan, Fukushima was the name of, you might have heard about that in your current events. Fukushima was is a city in Japan where they had a nuclear plant, and it was on the coast of Japan. And so whenever the tsunami hit, tsunami sent this huge tidal wave in right on the coast where those power plants were, the nuclear power plants, and completely disabled the power, shut off all the power to it, flooded it, and so basically they couldn't get those control rods in to stop the plant. And so it got overheated, got really hot, and so they started just trucking water, lifting water in from the ocean, pumping water in from the ocean to cool this off. But that contaminated the water, and the water leaked out, and so now there's this contamination, this nuclear contamination all around that area. Walk around here to check my time. I'm going to have to stop here. I think I want to keep these under 15 minutes, so I'm going to pick this up in just a second.